In this video, we'll be presenting our work on key handshape discovery in sign language videos. We'll begin by explaining the need for extracting such visual units that compose sign language and present our correspondence autoencoder-based methodology.
Sign language is the native language of the deaf, and each deaf community uses its own sign language to communicate. Recognition of sign language is a difficult task which often requires tedious annotations by sign language experts. Today, these annotations are performed using tools like Eland Linguistic Annotation Tool and SignStream tool that is designed to facilitate linguistic annotation and analysis of video data from American Sign Language. In this study, detection and annotation of key handshapes, which are meaningful visual basic parts of signs in a sign language, is applied using unsupervised machine learning techniques and end-to-end neural network architectures that have proven success in unsupervised discovery of subword acoustic units in speech processing are also used. A sign is one of the basic elements in a sign language that embodies a meaning in a sentence. A sentence in a sign language can be considered as a sequence of different handshakes performed one after another at different locations around the body. It may be composed of an initial handshape at some location around the body, external or internal motion of the hands, and a final handshape at some place around the body respectively. A sentence is composed of signs performed one after another. In this study, we coined the term key handshapes. Key handshapes are the meaningful visual basic parts that are one of the many key components of a sign in a sign language dataset. Handshapes are used in both algorithmic and linguistic studies. Although knowing the key handshapes is not enough for understanding and explaining the information to be conveyed, it's an important delimiter for annotating and breaking down a video sequence into meaningful parts. Frame-level annotation helps determining key handshapes in a sign language, which in turn allows creation of the lexicon of a particular sign language. In addition, frame-level annotation of key handshapes lets us summarize signs by means of a sequence of key handshapes. Also, it helps better aligning of similar sign videos.
The methodology follows an encoder-decoder structure in which the key handshape frame assignments can be obtained. This methodology has recently been proposed for acoustic unit discovery task in speech. The main novelty brought with this methodology is that it's a neural network-based clustering, which in turn may be expandable to other improvements such as recurrent structures or adversarial training methodologies. The posterior distribution over the set of key handshapes to be discovered is obtained after some encoder. And this vector is used to regenerate the input frame since the problem is defined to be unsupervised. The training loss is the reconstruction loss and the sparsity cost applied on the intermediate layer such that the distribution over the set of key handshapes are forced to zero out the irrelevant ones. This is why we call the structure sparse autoencoders, meaning SAEs. In this study, we used two features as input X: histogram of oriented gradients HOG and ResNet 18 bottlenecks. This figure shows the P-layer activations right after the encoder. Each frame gives an estimate of the posterior probability distribution over the set of key handshapes given the input. The correspondence in the title of our study comes from the fact that we also decode frames that are assumed to correspond to the same key handshape. This is obtained by aligning videos of the same sign using dynamic time warping. Therefore, in SAE, meaning autoencoder training, the input and the output are the same frames, while in co-SAE, meaning corresponding sparse autoencoders, the input tries to produce a corresponding frame. In this figure, we see two key handshapes that produce each other. The flowcharts of the SAE and the co-SAE can be seen on this figure. The middle layer activations give us the key handshake assignments.
As baseline clustering methods, we used K-means clustering and deep clustering. K-means clustering is a simple and well-known unsupervised machine learning algorithm. A cluster count, in other words, the number of centroids, is to be decided. Initially, the samples are randomly grouped into K clusters. Then, the algorithm iteratively finds and enhances the clusters by minimizing the mean squared error of each cluster. A centroid is the imaginary or real location representing the center of the cluster. Deep cluster is a clustering method proposed by Karen et al., which jointly learns the parameters of a neural network and the cluster assignments of the resulting features. It iteratively groups the features with a standard clustering algorithm and uses subsequent assignments as supervision to update the weights of the network.
Since the training is conducted in an unsupervised fashion, there's no way to know exactly the actual number of key handshapes and which index should correspond to the actual key handshape. One commonly used metric to evaluate clustering is the normalized mutual information, which gives a value between 0 and 1. Another intuitive metric is the estimation of accuracy, which we'll describe next.
Let's have a look at the following example to understand how we apply the accuracy estimation, where a dataset of 29 samples and 3 classes. On the left-hand side of the image, the data is clustered into 5 clusters. The observer checks every cluster one by one and decides on which class would be detected by the cluster. Initially, the observer doesn't know how many classes there are in the dataset, and as she observes the samples, decides to assign a new class or assigning a cluster to a pre-allocated class. Initially, the observer sees cluster 1 and assigns a new class with red blocks while assigning all the samples in cluster 1 into class 1. When observing the cluster 2 and cluster 3, observer assigns new classes. When observing cluster 4, the observer assigns the cluster to pre-allocated class 1. And finally, the last cluster is assigned to the third class. In our case, the number of samples is 20K and the cluster count is 256. And the observer sees only 10 images per cluster as a group of images. Hence, the observer performs 256 annotation, but 20K images are annotated and 27 key handshapes are found to create the lexicon of the dataset at the end. The accuracy shows the result of classification after the clusters are assigned to classes. All the detailed information about the dataset and experiments can be found at the websites shown in the slide. The dataset includes 11 signed sentences performed by 6 different users. Each signed sentence is performed by a user 5 to 7 times, resulting in 400 signed videos. There are 20K images assigned to 27 classes. The initial, final, and transition frames are not in the 20K images. We have experimented with various cluster numbers and sparsity weight values. We obtain good results using the parameters provided in the table. Since there is no means of validation and early stopping in our unsupervised setting, and the main objective of a high frame accuracy rate is different than the training loss, there is no early stopping criterion available, and hence we trained all the models for the same number of epochs. The result table gives us the frame accuracy rate and the NMI scores of the proposed methods compared with the baseline. We also included the performance of the ordinary k-means clustering with Euclidean distance and minimum mean squared error cost, since it could be considered as a natural baseline for clustering applications. It can be observed that handcrafted histogram of oriented gradient features yields better performance than ResNet 18 bottleneck activations, which were trained on ImageNet data. One interesting observation is that the improvement brought by the collaborative training is more significant on ResNet 18 bottlenecks, although it also improves the results with HOG. Overall, the best accuracy is obtained with correspondence sparse autoencoder and HOG features. Using the NMI metric also indicates the same results. Correspondence sparse autoencoder gives the best key handshape labeling results.
In training, our experiments show that after one pass over the dataset, with the autoencoder training, the convergence is obtained and no further improvements in accuracy is observed. However, if we fine-tune using corresponding pairs, after the autoencoder training, we obtain further improvements both in the accuracy and the NMI metrics. Furthermore, going back to autoencoder training, after correspondence training, we get the improvement even better. This shows the effect of COSAE, meaning correspondence autoencoder training, in terms of escaping the local optima on the autoencoder training.
In addition to accuracy and NMI metric, we examined the confusion matrix to see the confused key handshapes. Looking at the representative frames given in the slide, we can conclude that using the histogram of oriented gradient features is expected to cluster these frames into same clusters and confuse them with one another.
To conclude, in this study, we have successfully applied the acoustic unit discovery techniques of speech processing to retrieve the key handshapes. The work conducted here provides an efficient, unsupervised way to label and summarize sign language videos. We have seen that this neural network methodology not only outperforms the conventional methods, but also could be extended to include recurrent structures and adversarial training as future work. Thank you very much for listening.